All right, welcome everybody to the last session of QIP, this year's QIP. Please take a seat. So we have the 8th section of complexity, so that's exciting. Let's have our first speaker, Yangjing Dong from Nanjing University. He's going to talk about on the computational power of QAC0 with superlinear ancillae. The floor is yours.
Okay, thank you very much for the introduction, and thank you all for coming here at the last afternoon. And today I'm talking about quantum circuit complexity for computing Boolean functions. And to be precise, the model is that to compute a Boolean function, we will put the input to the left side of the circuit along with some ancillary qubits initialized to the 0 state. And we will apply several layers of quantum gates, and at the final state, we will measure the first qubit of the output state in the computational basis and expect that the measured outcome is the function that we wish to compute. And in quantum circuit complexity, the problem that we are concerned about are lower bounds on, for example, depth and size for computing Boolean functions such as parity or majority, and etc. It's easy to verify that in quantum circuits, the number of inputs plus the number of ancillas times the depth is approximately the size of the circuit. So instead of giving size lower bounds in this work, we will mostly talk about ancillar lower bounds. For local quantum circuits, there is a well-known technique that's called light cone arguments that can give lower bounds for local quantum circuits. The general idea is that, for example, if a quantum circuit consists of only 2 qubit gates, then the output of a depth D circuit depends on only at most 2 to the power of D inputs. And for most reasonable functions that we consider, the output should depend on all inputs. So we have 2 to the power must be at least n, and this derives to the depth lower bound of log n. This is all good for local quantum circuits, but if we have, for example, unbounded finite gates, then this argument does not hold, because, for example, in this example, the large control Z gate will directly relate the output of this circuit to all the qubits, including the inputs and the ancillas. So we need new techniques to prove lower bounds for non-local quantum circuits with unbounded finite gates. And for this talk, we can first look back to classical shallow circuits. The complexity class AC0, which consists of circuits consisting NOT gates and AND or OR gates with unbounded fan-in. And the depth is constant and the size is polynomial. The famous switching lemma of Hastad already proves that with AC0 circuits of polynomial time, we cannot compute the parity function. So in this work, we consider the quantum generalization of AC0 circuits, which are QAC0, introduced first by Moore in 1999. It consists of all the control Z gates, which is a quantum generalization of the classical AND gates, and has the effect when applied on a quantum state, applies a phase flip if the state is all 0 and does nothing otherwise. The depth is also constant and the size is polynomial. So the question here is now we consider is parity in QAC0 circuit? So or can QAC0 circuits defined in this page compute the parity function? The conjecture is no. QAC0 circuits cannot compute parity, and there has been a lot of works. For now, we know that to compute parity exactly, we need at least a linear number of ancilla, and to compute exactly with those 2 circuits is impossible even if we have an unlimited amount of ancilla. In 2021, Rosenthal have also generalized this result to the average case and proved that to compute the parity function in the average case, you cannot also achieve it if the depth is only 2. In a very recent result of Nadine Pauli, Farhan, Vascon, Chancellors, and Yuan, they have proved that to compute the parity function in the average case, the ancilla numbers must be at least n to the power of 1 over d, and this is the first polynomial ancilla lower bound for computing parity in the average case. And it's also noteworthy that Rosenthal has also proposed a DAS7 circuit for computing parity, which uses exponential numbers of ancilla. In this work, we give new lower bounds on this problem. So we prove that for any QAC0 circuit with DAS-D and ancilla size A that computes parity with an average case error that's strictly smaller than n-half, the ancilla must be at least n to the power of 1 plus 3 to the power of minus d. And we can see that as long as d is a constant, then this term is slightly larger than linear. And hence, in the title, we say a barely superlinear lower bound. Although this lower bound may seem still far away from our conjecture that any QAC0 circuits with polynomial size cannot compute parity, our second result surprisingly shows that this lower bound is actually very tight. We prove that if we can improve this lower bound slightly, for example, if we can improve a lower bound by changing the exponent from d to d over log d, then this implies QAC0 circuits of any polynomial size cannot compute parity. So I draw the results in a line where the axis is the ancilla lower bound, and the goal is to prove an arbitrary polynomial lower bound. Previous results shows that to compute parity function in the average case, we need at least n to the power of 1 over d ancilla, and to compute parity exactly, we need at least linear ancilla. In this work, we point two new points here, and the left one shows that towards the goal, we are already here. We have a barely superlinear ancilla, and actually, this is very tight. The barrier is just ahead of us, and as long as we can improve a little bit and beat the boss here, the way towards any polynomial ancilla lower bound is straightforward. So this is the main results, and the other results include the ancilla lower bounds for other Boolean functions, such as majority and mod k, and also ancilla lower bounds for other quantum tasks, for example, quantum state synthesis and channel synthesis. To dive deeper into our results, I need to introduce the notion of approximate degree of quantum operators. And we call an operator P has degree D if it can be written as the sum of the operators Pi such that each Pi acts non-trivially on at most D qubits. And the approximate degree of P is defined to be the minimum degree of an operator Q, such as it is epsilon far from P within the spectronome. So I now state the main technical theorem of our work. Let U be the unitary of a QAC0 circuit with DAS-D and A ancilla, and A be any measurement operator with degree L. And then for some epsilon, we prove that the Heisenberg-evolved measurement operator U dagger AU satisfy a approximate degree upper bound as in follows. And the important thing to note is that if L is sublinear and D is a constant, then this upper bound is also sublinear. The Heisenberg-evolved measurement operator U dagger AU can be seen as the overall measurement effect if we apply the operator first apply the unitary and then apply the measurement A. And we can use this main theorem to the task of computing Boolean functions because we know that when computing Boolean functions, we only measure the final first qubit of the final state. So the dimension of A will be 1. So as a corollary, we prove that if P is the polynomial that describes the probability that a QAC0 circuit outputs 1, then the approximate degree of this polynomial is also upper bounded by this term. And also if D is a constant, then and A is not that far from a linear, then this upper bound remains sublinear, sorry. And in construct, we know that the parity function has approximate degree omega n. So this readily can prove that QAC0 circuits in this case cannot compute the parity function. And I want to know that this generalizes the result of approximate degree of linear size AC0 circuits, and this is nearly tight because there exist linear size AC0 circuits with this approximate degree. So to prove these approximate degrees, actually, I will split the proof into two steps or two cases. The first case is for quantum gates that are small, for example, the arbitrary single qubit unitaries and the CD gates that act on, at most, some T qubits. And the observation is that for the Heisenberg-Evolved measurement operator U dagger AU, the unitaries that not touch a local term A will cancel out with each other. So U1 dagger times U1 is identity. So the fact is that if we apply a layer of small gates that each act on at most T qubits, then degree of U dagger AU is at most T times the degree of A. So this can be seen as a light cone argument for local qubits. And we know that the hard part will be how we handle the large gates in a QAC0 circuit. And here is where the approximation degree comes in. So recall that the definition of a control Z gate, which applies a phase flip to the old one state and otherwise does nothing, if we write it in matrix form, then it is a diagonal matrix with all ones except 1 minus 1 on the right bottom corner. So we can write CZN as identity minus 2 times the O1 state. And we can use a very handy result that states the approximate degree of the O1 state instead of being n is square root n. So as a corollary, we can prove that the approximate degree of the control Z gates acting on n qubits is at most square root n. So for a layer of large CZ gates, suppose UI each acts on T qubits, then we can upper bound the approximate degree of U by the sum of the approximate degrees of each UI. And here we note that because each UI acts on at least T qubits, and there are at most n plus 8 qubits, so the number of such gates is upper bounded by n plus a over T. And because each UI has approximate degree at most square root T, the approximate degree of U can be upper bounded by n plus a over square root T. And applying this bound to the Heisenberg-Evolved measurement operator, we can get that the approximate degree will get added by at most an factor of n plus a over square root T. So putting this together, we can prove an upper bound of the approximate degree of a layer of different size quantum gates. So we can choose T to be a threshold, and suppose U is a layer of different size gates. We let US be the gates that act on at most T qubits, and UT be the gates acting on at least T qubits. So the approximate degree of U dagger AU will be upper bounded by L times T plus n plus a over square root T, because the small gates will multiply degree amongst a T factor, and the large gates will add the degree by at most n plus a over square root T. Optimizing over T, we can get a desired upper bound, the desired approximation degree upper bound, which is the original approximate degree of a to the power of 1/3 times n plus a to the power of 2/3. And this is what we do with one layer of different size gates. And generally, we know that a QAC0 circuit can have a constant number of layers, so we apply this upper bound repeatedly. So we know that initially the approximate degree of A is L. After one layer of quantum gates, we know that the approximate degree now becomes n plus a to the power of 2/3 times L to the power of 1/3. And repeatedly applying this upper bound D times, we can get the desired approximate approximate degree upper bound, which is n plus a to the power of 1 minus 3 to the power of o minus d times L to the power of 3 to the power of minus d. So this is the approximate degree upper bound for Heisenberg evolved measurement operators. And if we consider the task of computing Boolean functions, then recall that what we do to compute Boolean functions is at the first we prepare the input x along with the ancilla qubit to the state 0 and apply the unitary u. And finally, we will measure the first qubit in the computational basis. So rearranging this equation, we observe that the polynomial p is exactly part of the diagonal entries of the Heisenberg evolved measurement u dagger times this term u dagger times state in 1 times identity times u. So this is then it is trivial because we can upper bound the approximate degree of p by the approximate degree of this Heisenberg evolved measurement operator, which is n plus a to the power of something slightly smaller than 1. For the worst case hardness, we can prove that the parity, the approximate degree of parity is omega n. So we can prove that for QAC0 circuits with slightly superlinear ancillae, they cannot compute parity in the worst case probability of 1/3. And the constant 1/3 can be improved to be a half with error reduction. And this bound holds for any Boolean function f such that the approximate degree is omega n. This includes majority and mod k. For the average case hardness, we adapt the same proof from MPVY24, which states that if U is a circuit with barely superlinear ancillae, then we cannot even compute parity in the average case. The proof is similar, except that in our case, our approximation is in the spectral norm, and in their proof, they only require a Frobenius norm approximation. So also for other tasks such as quantum state synthesis and channel synthesis, we can adapt the same techniques and get some approximate degree upper bounds. So the final thing I want to talk is our final result that shows that if we can slightly improve our lower bound, then any QAC0 circuit with polynomial size cannot compute parity. And this is proved by a contradiction. Suppose there exists a constant c such that n to the power of c ancillae can compute parity. Then for any k, we will construct a circuit family with that CDK, and the ancilla is n to the power of 1 plus 2 to the power of minus k. And we observe that the depth grows linearly over k, while the number of ancillae grows reverse exponentially. So we can choose k large enough, and because our lower bound is of the form 1 plus exponential minus small od, we can always choose a k large enough that violates our lower bounds, and this leads to a contradiction. So how do we construct this circuit? Actually, the idea is very simple. This is because the parity function can be computed recursively. So if we have a circuit un that computes the n-bit parity, then by using 2 instances of un, we can compute the parity of two n qubits by these circuits shown above, and the depth only increases by 1. The input size is multiplied by 2, but we show that the ancilla size relative to the input size is decreased. So using this idea, we can construct carefully a tree of k layers of different circuits that compute the parity for different parameters, and carefully choosing the parameters, we can achieve what we have said. The depth is k times CD, and the ancilla relative input size is only n to the power of 1 plus 2 to the power of minus k. So this is all that I have to talk, and the open problems, of course, include whether is it really that QAC0 circuits cannot compute parity, And what is the approximate degree of QAC0 circuits? This is potentially a hard problem because this is also open for AC0 circuits. Thank you.
Thank you very much for the talk. Are there questions?
Sure.
In the paper, so I've read the paper. One of the implications is that regardless of what state you start with in your ancillas, you still have low degree. You still can't do parity.
Yeah.
Right. Can you just say a little bit about that?
Sure. That is actually purely mathematical. So, like, recall that the approximate degree is defined in terms of the spectral norm. So, if you restrict some part of a matrix to be an ancilla state, then the spectral norm of the restricted matrix will not increase. For example, if you have a matrix A and you restrict the some final k qubits to be some arbitrary states, and then the reduced operator, the spectral norm will not increase, will just decrease.
Thank you.
So I remotely recall that there's a similar result, bootstrapping result for TC0, which claims that if you can use TC0 to compute, is it a group composition? I think it's group multiplication problem, slightly better than the current lower bound. You can prove slightly better lower bound than the current lower bound. Then that lower bound can be all the way bootstrapped to super polynomial lower bound. So, but since that bootstrap argument, we don't have any we don't have any idea how to reach that point. So, do you think the same will hold for your result as well? How do you judge the difficulty for reaching the bootstrap point you provided here?
Actually, we think, if I'm not remembering wrong, the bootstrapping techniques you mentioned is quite similar to ours, and we have tried our best to optimize the parameters, and this is what we get right now. So to use these similar techniques to prove parity is not in QAC0, I think we may need some other techniques because, like the second open problem, the approximate degree of QAC0 circuits actually is very hard.
So you think we already reached some kind of barrier here?
Yeah.
Current technique may not work. Okay.
Yes.
Thanks.
Hi. So I'm wondering if you've thought about it seems like if the approximate degree of and happened to be below root n, then the result you'd get a slightly better result. Yeah. Have you thought about
So you mean
if there was some other, say I gave you some other gate acting on many qubits, if you could show that it has approximate degree below some threshold, is there some threshold where if you show that a gate has approximate degree below that that plus single qubit gates can't do parity?
You mean for the control Z gates, the approximate degree of control Z gates?
Right. You said those were root n, right?
Yeah, but the approximate degree of control Z gates is square root n, and I believe that's tight.
All right, I'm saying if somehow we were thinking about a different circuit class that was single qubit gates plus another many qubit gate.
Yeah. Okay.
If we knew that it was if its approximate degree was below some threshold, do you know if there's some threshold where if it's below that then you can't do parity?
Okay, if we want immediate results, then the approximate degree will be log n. So as long as it's polynomial, then I think we will still get some. What we can optimize is the constant 3 here. So we may change 3 to 2 to 1.5, but still it will be similar.
Oh, okay.
Yeah.
So it would need to be log n?
Yeah.
Okay, thank you.
think we're perfectly in time, so let's thank the speaker again. We have a few minutes break until the next talk. Next speaker can prepare.